that there are shells. First of all, the behavior of atoms is determined by their electronic structure, where the electrons are. And this is the so-called shell model. And that is, as you put electrons into an atom, those electrons go into orbitals. And these orbitals comprise shells. And you get different shells with different periodicity. So here's the first shell. We put electrons in. Here's a filled shell. We then go to the next shell. And on average, that means the electrons are a little further away from the nucleus. And the outer shell is the one that determines the properties. The electrons that are in here determine chemical properties. And that's very important for understanding how matter is built up and how matter actually, the properties of matter. Now we're going to another larger shell. This is sodium. This is lithium. This has, if you look at the outermost shell, there's one electron. Lithium, there's one electron. That's why they have similar properties. Those electrons in the outer shell determine the chemistry, and that turns out to be an interesting property of these various atoms. So these valence electrons then determine chemical properties, and here are some of the groups that are important. Carbon is one of the central atoms as a building block. Organic chemistry, which originally got its name as the chemistry of life, because life forms have carbon as the central atom. And carbon has very unique properties which make it extremely important. It gives the most diverse number of molecules and compounds, and so it's a center of a branch of chemistry. But then there are these other atoms that have these different properties that are the building blocks of matter in general. So the way in which these building blocks are held together is very important, and there are two ways in which they're held together. So as I mentioned, when you have an atom, you have protons in the nucleus and electrons around that nucleus. And the nucleus is much more concentrated than the electrons. The electrons are spread out. Electrons have very interesting and unusual properties. Now, I should point out, by the way, that the perspective that we're going to look at is that everything, this table, trees, you, are made up of molecules. And one of the unusual features is that when you look at molecules, they're very small. You can't quite see them. And mostly there's empty space. And it's very different from what you see. You know, a table looks hard, it looks real, but it's mostly empty space. In fact, there's a recent BBC program in which it was pointed out that if you take the organic compounds, or all the compounds that make up all the 8 billion human beings on Earth, and take away all the space, you'd have about a sugar cube worth of matter. So most things are really odd. I mean, imagine that. A solid table is mostly space, empty. You're mostly space, empty. You're mostly water. Take away all the space, and it becomes very small amount of material. This is a very odd picture, and we're going to see why that's important. So it's nothing like what you normally encounter. It's a really odd way of doing it. And why do chemists do it this way? Because experiments lead them to this, and that's sort of the conclusion, this sci-fi view of the universe. It's really odd because it's nothing like what we ordinarily see. That's kind of interesting. You might say, well, it's science fiction. Who cares? Well, you'll see that it has really consequences. This very peculiar notion, which is driven by experiments. All these ideas come from experiments and accounting for them. Okay, so how do these atoms, which are the building blocks, combine to make tables, to make plants, to make you? There are two major ways. One is two atoms can come together. One gives an electron to the other. An electron is negatively charged. A proton is positively charged. Each atom is neutral. If we take away a negative charge from something that has no charge, we're just left with a positive charge. If we add an electron to something with no charge, it now becomes negatively charged. So we have plus and minus. Plus and minus attract. That's called an ionic bond, and that's one way in which things are held together. Salt, sodium chloride, is held together that way, by an ionic bond. Dissimilar charges attract. Same charges repel, but dissimilar charges, plus and minus, attract. Another way in which atoms combine to form larger aggregates, molecules, is by sharing electrons. One doesn't give the electron completely to the other, they share. There's a cooperativity, and both atoms are happy as a result of that. And covalent bonds are mentioned here, and that's an extremely important way of bonding. That's probably the most common way for organic compounds. Well, it is the most common way for organic compounds, the things that make up us, organic compounds. So this is a general idea that I've said, that molecules now are aggregates of atoms held together mainly by covalent bonds for most of the compounds that we're interested in, although rocks are held together by ionic bonds, sometimes covalent and ionic. And we can account for and have pictures of molecules like octane. Octane is gasoline, the major component of gasoline. This is water. This is very peculiar. It doesn't look like water that you ordinarily see, but this is a chemist's view. We have two hydrogen atoms and an oxygen atom held together by covalent bonds. This one over here is DNA. That's what has the genes that determine, to a large extent, what we are. And this very complicated molecule has all these covalent bonds, and it's an important way of determining life. Who we are, or whether we have, depending upon the DNA, whether we have bacteria, whether we have humans, whether we have plants. And to understand this very complicated system, by the way, you've heard about this. This is a double helix. So they have two spirals wound around each other. There's one spiral, there's another spiral wound around each other. It's a really interesting structure that was first discovered by Watson and Crick and provided us with a chemical understanding with the basis of life. How it's determined who we are, how these genes work. And to understand that, we have to have this very peculiar picture of the universe, and we'll see that that provides an understanding of biology as well as chemistry. Biology is really chemistry. Okay, so here, as I said, are these models about covalent bonds, and the way in which you can view how these are held together is that plus and minus attract. If we have a nucleus that's positively charged, another nucleus that's positively charged, and we have electrons that are shared between them, these two electrons that are shared provide an attraction. The plus and the minus, and the plus and the minus attract. Even though two pluses would repel each other normally, because we have electrons between them, there actually is an attraction. It's as simple as that, and very powerful. So one of the things actually that's interesting about chemistry is that the ideas are really simple. Opposites attract, plus and minus. It's a really simple idea. But the structures that chemists draw, and you'll see a lot of them, are very complicated. It's sort of like a shorthand. It's like hieroglyphics. Try and interpret what chemists mean by that. It's like learning another language. And it turns out that there are some hidden things in that are important, and it's a shorthand way of writing very complicated molecules and providing some understanding. But the ideas are really what we're going to talk about here, about where this comes from. So here we have the electrons spinning about, and the more negatively charged electrons between the positively charged nuclei, the stronger the bond is going to be. And so if we have 2 electrons shared versus 4, 4 is going to be stronger than 2, and it's really that simple. And there are some other details that we needn't worry about. There are some odd properties of electrons. They also have a property that's called spin, which turns out to be important. And the way in which people treat this, theoretically, is very important. So people have come up with ideas, theories, about how this bonding occurs, which are very powerful. And what's nice about that is that if you like computers, you like using computers and doing computations, you can actually calculate a lot about these models, these atoms and molecules we'll be talking about, what their structures are, what their properties are, and that's a very attractive thing, and it's based on quantum mechanics, which is another very odd thing. And Einstein, by the way, didn't like quantum mechanics. The basis of quantum mechanics is the Heisenberg uncertainty principle, and you deal with probabilities. And Einstein thought God doesn't play dice. He doesn't take chances. He didn't like it. But it turns out to be very powerful and very useful. Why? Because it predicts things. And that's the whole idea about chemistry. Is we use experiments, we conjure up these very odd notions that I'm going to tell you, that I already told you about. And then that enables us to predict things. And if the predictions turn out to be true, then we like the theory and we keep it. If it turns out not to be true, we just come up with another theory. This is sometimes called the Greek method. This is part of the Greek heritage. The Greeks love making myths. So one makes these hypotheses and myths, and I guess so. Good sake. Okay, so this now is sort of a detail about one of the atoms that has its fluorine. Fluorine is a very interesting atom that has very important properties. One of the interesting things about fluorine, it's good for your teeth because calcium fluoride is a very hard substance, and you make calcium fluoride that actually has an ionic bond, but it can also form covalent bonds. And this is just an illustration that what happens is the fluorine share, each donates an electron to share to form a fluorine molecule. And there are some magic rules. Remember I said that you fill up shells. When you fill up a shell completely, that's sort of chemical nirvana. So atoms are very happy when they have filled valence shells. And there are magic numbers for filling those valence shells. So 8 is a magic number, and fluorine here is very happy. So is the other fluorine, which also has 8. So by sharing, they both accomplish the purpose of having so-called filled valence shells. explains their properties, and this is just the way that chemists abbreviate it, that covalent bond that attaches the atoms to each other. And this then is just a statement, this really simple rule that comes from theory. Now, molecules, or let's say atoms, are very nervous. They're always moving. So they vibrate, and this just gives you an illustration of that. The other thing is you'll notice their colors here. The colors indicate where the electrons are. The electrons are moving around, and that creates a charge distribution, which is very important, because as I mentioned, positive and negative attract, positive like charges repel, positive, negative, and negative. And this is very important for interactions between molecules. So this kind of idea, a pulsating atom, is really a better description of what's going on. Now, what we do then is, by connecting atoms to build molecules, and we're able to determine structures of complex compounds. So, as I already said, there's a problem with doing that, and that is chemists have shorthand ways of making these pictures. That pulsating egg, if you like, was a more realistic drawing than what chemists do. Chemists do shorthand to show where the bonds are. And why do chemists do that? Well, we want to know the structure, the molecules that make up nature. And once we're able to determine the structure, or have an idea about the structure, that means we know something about the properties of the molecules. And when we know something about the properties of the molecules, we can design materials that are going to be useful. For example, it used to be said that at the end of the last century was the age of plastics. And that's a material that turns out to be very useful, and we use it today, all kinds of different materials. I'll talk about the materials that are probably the most exciting today, nano materials, a little later on. But at any rate, we can make things that are going to be useful, that have new properties, that are lighter weight, that are stronger. Tires have aramid fibers in them. Aramid fibers are very strong, and they're an example of materials. And if we understand something about structure, which leads us to predict properties, we can then make those materials, and hopefully we'll be right about the properties and have something that will be helpful to people. We can also understand how drugs work, but even more importantly, we can design drugs that will be good for curing diseases, alleviating pain. This actually, we'll see more of this in a moment. We can actually, an interesting thing about the structure is we don't have to have the thing in our hands to determine what the structure is. We can determine the structure of things that are far away in outer space. We can also determine what products are formed in biological systems. We can determine what's found in nature, in the environment. And that can be very important because we'll actually see an example of, well, I'll tell you a good example of this. A good example of this is CO2 in the environment. CO2 is a greenhouse gas that's contributing to global warming. And we can analyze that. We can see it. We see the amount of CO2 going up. We see the temperature, average temperature around the world going up. And that, as we'll see, is very important. So we can monitor that, and hopefully, now that we know about it, we can prevent it. Another example, by the way, is the ozone hole. So the ozone protects us from ultraviolet radiation. And And we're able to see that ozone hole, which is up in the stratosphere. So there was a hole in the ozone layer that's protecting us, and it was actually being destroyed by freons. Freons were used for cooling refrigerants, and it turns out one of the reasons they were used is they're very unreactive. No one thought they would do anything. Well, it turned out they react in the ozone layer and were destroying the ozone. And we found out about that, and freons now are no longer used as substitutes to prevent that. And that's a way in which we can make the world a safer and a better place to live in by being able to determine the structure and changes and seeing what's happening to our environment. Another one that's very popular, I know how popular it is in Japan, but in the US, there are all these crime shows. And that's where DNA is used in investigations. And DNA is actually wonderful because it does two things. One, it can tell you if somebody had, who the person was that committed a crime. DNA, we all have essentially unique DNA. It's better than fingerprints. And what's also interesting is people who are wrongfully convicted, now that we have DNA analysis, their convictions are overturned. They didn't do it, and it's proven by somebody else's DNA, not theirs, is there. So that's another practical application of understanding chemistry, knowing something about structure, what we can do with it, and we'll see this in more detail in just a moment. So shown here is the build-up, a way in which we're going to go from atoms, molecules, to the large world that we see. So we're going to go from the chemist's view, which are things that are strange, mostly empty space, and then all these unusual materials, and we're going to go to the real world. And the way chemists did it was starting with the real world, macro world, going to smaller and smaller particles, getting to a molecular level, going to the atomic level, and as I say, the atoms are built up of nuclei and electrons around them. And now what we're going to do is go the other way around. And that is, this is how we got there, this picture of this chemist's view of the world. And now what we're going to do is take the chemist's view and be able to predict the properties of molecules, know what molecules we can make and how to make them, see what the particles properties will be, and the species that we can really see. What are they going to really be like? So part of this, chemistry is a central science, meaning that chemistry is going to bridge physics. So we're starting here with sort of a physical view of the world, and quantum mechanics really came from physics at the 1930s, last century. And we're going to combine that, and one of the things we're going to do is go to biology, go to actually engineering, material science, and see that chemistry plays a central role in all of this. And depending upon what your interests are, I mean, everyone should, in my opinion, everyone should learn something about chemistry or science in general, because that's the world we live in. You can better understand what the world is and how to make it a better place if you understand some of these really odd ideas, but where they come from and what you can really do with them, what is real and what isn't real. And so here we go. What we're now going to do is we're using this predicting properties. We're going to determine structure. And here's the way, first I should say that the challenge is, how do you determine structure? By the way, I stop and ask if there are any questions. Anyone has any questions about this? This should be interactive, so feel free to ask questions. Practice English. Don't ask me in Japanese. I won't know what you say. Yeah, sure. Yes. Yes. So it turns out that we do organometallic chemistry. I should say that even biology, there's what's called quantum biology, where people are using quantum mechanics to predict biological properties. The problem with that, the molecules are so big, it's hard to do the calculations. So we do calculations as well, quantum mechanical calculations. But to do exact quantum mechanical calculations are very hard. So what people use are approximations. And in our case, we use a method called DFT. And the idea behind that is it's an approximation to a quantum mechanical solution. And it turns out that it really works better than it should, because what people believe is the errors cancel, so that if you try to make it better, it actually gets worse. So an exact solution would be ideal, and maybe someday the computers will be large enough to do exact solutions. But for now, even for organic compounds in general, you have to use approximations. So, density functional theory, DFT, is one of those approximations. But here's a challenge for young people. If you're interested in that, you come up with a better way of doing the calculations. So there are two approaches. One is, sometimes what people do, and we do this, is we have some big molecule that we want to do a calculation on, but it would take too long to do the calculation, a rigorous quantum mechanical calculation. So sometimes what we do is we make a simple model, do a rigorous quantum mechanical calculation, and then put that in the bigger one, and see if we can make it better, and have better agreement with the properties of the material. And it's a big challenge, and it works. And one of the most amazing ones is DFT, which everybody knows it's wrong, but it has these, it's just sort of wonderful because the errors seem to cancel. But the message here is you can't use it on everything. You first have to make sure, validate it for the system you're working in, then apply it to something new. Why do you want it to, something new? You want to predict the properties. And it turns out to make things is very hard. That's very important. That's very hard. It takes a lot of time, a lot of work. To do the calculations at a DFT level, relatively fast, as long as they converge. It's relatively fast. And now you can see if the properties are predicted to be what you want. If not, do another calculation, find something that you really want to make, and then you go and make it. And if it has the right properties, that's wonderful. That's what we do in our research. And I would say that it turns out to be really useful, a great time saver, and a way to get to something that's going to be really useful very fast. But that's the challenge. So, so one of the exciting things is there are a number of challenges in chemistry for young people. And if you really like theory, you like doing high-level quantum mechanical calculations, being able to get better theoretical treatments of more complicated molecules would be really important. One of the things we're going to talk about, one of the hot areas now are surfaces. In the old days, not very much was known about surfaces. Surfaces turn out to be very important. Things happen on surfaces that don't happen in solution. And why is that? What goes on the surface? Well, no one knew. It was sort of black magic. Now you're going to see pictures that we now have of surfaces where we have a better understanding of what's going on. And but that's a major challenge. If you can understand surfaces better, that can be very important. And that's one of the challenges. So it's kind of exciting times. What I hope you'll see in this is that there's some real breakthroughs that are going on, which you may want to become a part of. Whatever your interests are. If you like making things, there are a lot of things to make that turn out to be useful and important. If you like determining structures, and you'll see how to do that in a moment, it's really spectroscopy is the major way. Again, being able to do this in a better way. So one of the ways about spectroscopy is X-ray crystallography. It's just a technique that's used for determining structures. And the trouble is, you need crystals to do it. So you have to have something that diffracts well. You need crystals that are big, and relatively speaking. If you have very small crystals, it doesn't work very well. So what do? You actually make the light stronger, so it's X-ray light. You use a synchrotron. So if you like doing synchrotron, this is great. So now, why does that make a difference? Well, it turns out that beta amyloid peptides are believed to be the causative agent of Alzheimer's disease. So Alzheimer's disease is the fourth major killer in the U.S. And it's a rather devastating disease, as you know, because people who get Alzheimer's, they essentially lose their mental faculties, and they need a lot of care. So it's very hard on caregivers as well. And the patient obviously can no longer think, but they live for a long time. And what happens is they form beta amyloid peptides in the brain, and that's the causative agent, it's believed, for Alzheimer's. And it's very important in the U.S. because the numbers are increasing because of the aging population. The oldest population in the world is Japan. And so I'm sure it's an increasing problem in Japan as well, and it's an exciting field to try to get solutions. The trouble with amyloid peptides is that no one knew what their detailed structure was because they didn't form large enough crystals. So a breakthrough has been for small models, not the amyloid peptides, beta amyloid peptides that are the causative agent of Alzheimer's, but small analogs of it. Very small crystals were made, and using synchrotron radiation, people learned something about their structure. So people have a better understanding of what amyloid structure is. And it's not only Alzheimer's, there are a number of diseases that result from this misfolding of proteins that causes toxicity. And so these are kind of exciting times because we're now developing the tools, and you can make even better tools for learning about diseases on a molecular level. And in fact, biology used to be a classification. You know, you count the number of legs that an insect has, a spider has, and so on, and you classify it. Well, that's interesting, but there was a big revolution in biology, which became molecular biology, because the structure of DNA was known, determined, and now people have developed tools for. It's wonderful if you like computer science. It's wonderful being able to use information that you can get from the genetic sequence, from the genetic code, to try to figure out what each gene does, what the gene is that causes Huntington's disease, how to be able to recognize that. This turns out to be, and hopefully it means that you'll be able to provide solutions in the future to genetic diseases, do something to alleviate or cure these. So these are exciting times because our knowledge is increasing so rapidly, but there's a demand for more. And it's going so fast because you have the intersection of physics, biology, computer science, engineering, as we'll see in a minute, for materials. So how do you determine structure? The main story is to use spectroscopy. And what spectroscopy does is looks at the interaction of light and matter. So here's just a pretty picture showing essentially a laser. And what you want to do when you shine light, as you know, if you can see through a glass window. If there's something in the window that absorbs light, you can't see anything. It becomes opaque. So why is that? Well, it actually depends on the structure of the material. The color that it is gives you some information about structure. So that's what we're going to do, is use the light that's absorbed in particular, to determine the structure of molecules. So it'll be a way to detect, identify, and see how much, for that matter, of these structures, of these molecules that we have. So there's a feature about light that is interesting. It is so-called electromagnetic radiation. It's a way of describing it in terms of physics, but the important thing is whether, so this is the various names we give to light. And here we're going to have a cell which we pass light through, and we measure the light that's coming out. Actually here, you do something else as well. Sometimes what happens is you put light in, and you get light coming out the other way, and that's fluorescence. So sometimes molecules absorb light, and you've seen this. Fireflies, they do it all the time. That's chemiluminescence. But you can actually shine light on some materials, and they'll glow with a different color light. And that also gives us information about these materials. So whether light is absorbed or passes through turns out to be important. And we have these different names for light, as you know. So it's centered on us, of course, and that's the visible light. And if you go to higher energy, so one classifies light in terms of energy, we have ultraviolet light. That's very dangerous, as I already mentioned. We have to be protected by the ozone layer from that, or by absorbing molecules, substances that will absorb light that we can put on our skin to prevent getting melanoma, skin cancer. And it turns out now in the U.S., UVA and UVB radiation has become very important for suntan lotions to prevent this deleterious effect, bad effect of this UV light. X-rays are even higher energy. We go the other direction and we get lower energy, infrared radiation. But anyway, those are just the names that are used. Actually, the one I like is if you go out here, there's microwave radiation. You can cook stuff with that. So molecules absorb microwaves. They shake, 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 shake. That means they get hotter and hotter and hotter, and you can eat. Of course, you don't have to do that. You don't put sushi in the microwave, but it's a great, fast way of eating. And then even further out are radio waves. And radio waves turn out to be very useful for getting structural information using something that you know about. Nuclear magnetic resonance is an excellent way that you look at the absorption in the radio frequency range, and that's an excellent way of getting detailed structure information. The way you may know about it is MRIs, magnetic resonance imaging. Magnetic resonance imaging is exactly the same thing. It actually, it's not so much you get structural information, you're looking at the relaxation of water in that case, but it's the same principle, and it enables you to see inside people. And X-rays used to be the way that it would be done, but X-rays, well, you'll see bone, but you won't see soft tissue. MRI, you can see soft tissue, and it's not dangerous, unlike X-rays, which can be give radiation damage. So here are all the words. Now we're going the other way. So this is a higher energy on the right here. And so we have gamma rays, X-rays, ultraviolet. There's the visible. And then the infrared, the microwave, and radio wave. And there are numbers associated with that. But the important thing is that from each of these different ranges, we learn more information. Oh, there's another thing about light. This is a nice thing. So it's like physics and chemistry, and that is, as I said, what chemists do, and physicists do as well, is we do experiments, and then we make up stories. And we have pictures of how things work. So light is one of those things that has a strange story. It's also true of electrons. And that is, light acts as both a wave-like thing, and it also acts as a particle-like thing. And so the particles are called photons, and you might say, well, wait a minute, how can be a both particle and a wave-like process at the same time? Is it schizophrenic? And the answer is no. Light is light. The problem is how we interpret the properties, what we see light doing. And the way that we can explain it is by saying it's got both particulate properties and wave-like properties. And so that's a challenge. Maybe you could come up with a better idea of how to view it, because that's the way we view it now. And it works. It provides good descriptions, but it sounds, why, how can it be two different things at the same time? It sounds strange. A lot of this stuff sounds strange, but because you can predict properties, because you can predict how to make things, it turns out these strange ideas are what keeps us making new drugs, new materials. And it's kind of exciting that these odd ideas really turn out to be from an impact on us, to be really important because of what we can do with it. And these are just more details. That's the energy scale. Okay, so spectroscopy is the process that we use. And so this is the absorption spectrum of ozone. We shine light. So this is about the visible range in here. And ozone appears to be blue, by the way. And there is absorption. We're measuring how much light is getting through. Here, all the light's getting through. But here, some of the light is being absorbed. And that tells us, that's a way of identifying ozone. Here's another molecule, ethanol. Okay, so why do they absorb this light? Well, it turns out that, as I said, properties of, starting with atoms, are determined by where the electrons are. And the electrons that I have described in terms of the periodic table are the ones that are called the ground state, the lowest energy form. But you can get excited, and atoms can get excited. And that means you can put the electrons in a higher energy state. And so when you put in energy, so light is a form of energy, you can actually, the electrons, or the atoms can absorb the light, go to this higher energy state. When the energy of the light exactly matches the energy of those states, that tells us we have, as you saw before, ozone, and that we have an excited state. So here's just a picture of what it looks like for an atom, which shows the electron distribution in the ground state, and here it's an excited state. They're just different, and the energy has to exactly match for the absorption to occur. Well, that enables us to do remote sensing, as I already mentioned. So here's a picture. NASA was able to use all these various instruments to determine the ozone layer, what else is in the atmosphere, carbon monoxide. They're able to show that. And this just shows where the energy states are in terms of, we talked about electronic energy, that's the visible and ultraviolet. And infrared, it's that vibration that we talked about. And seems to be there we go. Okay, and this is just telling you the various spectroscopies they use. And you can see this is remote sensing, and you can tell what's in a star by looking at the absorption. Here is a solar spectrum. So why do we care what's in a star? Well, one is curiosity, but the other reason is more important, and that is this is a star that's near and dear to us. This is the sun. And this shows that what the radiation coming from the sun is. And we can tell what actually is causing this. That's one thing, so we know what's present in the sun. But more importantly, that's what comes to us on Earth. And so far as sunlight. And the importance of that is that if we can capture the energy from sunlight, we can help alleviate the energy crisis that is coming. And shown here, before we talk about the energy crisis, is so what you've seen is that spectroscopy enables us to determine structures. And once we know structures, we can correlate those with properties. And we can predict for new structures what the properties would be. We also can design syntheses. Take two molecules, let them react. We can predict what the product is going to that, and as I mentioned before, new plastics or new drugs and many other things. And shown here are you can't see them, but it doesn't matter because they're very cryptic. These are the top 200 drugs in U.S. retail sales, and they're very complicated structures, but chemists, looking at those structures, well, first, they're able to predict which structures they should make, and that'll have the properties that we want. And so, for example, let's see if I can read this. This first one is Nexium. So this, and Nexium we're all familiar with for ulcers. And then this is Lipitor, used for heart treatment. And the next one is Pronix, also for heart. And you can see these are sort of complicated drawings and hard to decipher. But chemists, this is chemical shorthand, and by looking at this, chemists can predict properties and get the property we want to help prevent heart attacks. This one is for asthma, Advair, and this is OxyContin, pain. This is Abilify, depression, Singular, asthma, and look at all these names. These are the top drug companies in the world. We have one for depression, we have another one for heart, and we have another one for depression. And all these, we can, by knowing something about chemistry, we can predict their properties, and we can do things that help people. Now, here's energy. The interesting thing about energy is that here we are about here, and what we're plotting is the amount of energy that's used in the world as a function of time. And what you see is over the next 20 years, there's going to be a tremendous increase in the amount of energy that is going to be demanded. And mainly, the increase in energy is due to the tremendous growth in China and India. And the rest of the world increases, but not as dramatically as China and India. This line represents the countries that are part of the International Energy Agency, Europe, European countries, US. So where do we get our energy now? Most of the energy comes from petroleum. And what the problem is, petroleum comes from oil wells, and based on the number of known deposits of oil, it was predicted that there would be a peak and then a decrease in the production of oil. And because of the financial crisis, we're probably reaching the peak now. It's expected to be 2010, but there would be a decrease in the production. There'd be this big shortfall. Well, it's not as bad as all that, as you'll see in a moment, but where are we going to get the energy from? This is actually very important in Japan. So Japan had gotten 30% of its energy from nuclear fission. All your nuclear plants are shut down. One may go back online. In 08, the council had voted to set up nuclear plants there. So many of the nuclear plants were closed down for refurbishing, but none have been set up again. So after the terrible incident in Fukushima, every time the nuclear plants are to get renovated, they don't get restarted. And that was 30% of the energy. And if they stay closed, that may not happen. They may open again in Japan. It's not clear. But if they stay closed, where are you going to get your energy? Well, the primary sources of energy are oil, natural gas, and coal. And by the way, nuclear fission is also a major energy supplier in France. 70% of the energy in France comes from nuclear fission. So this is a projection by the same international agency. One of the things you see is that oil is going up. I just told you there's going to be peak oil. And that's for the known oil supplies. And there are some new sources of oil. There are some new discoveries. For example, in the Arctic, there's oil that Russian ships are going out into the Arctic to drill the oil. And so they're new discoveries. They're deep sea oil off the coast of Brazil. There also is oil that is being produced. But the major other source are tar sands, unconventional sources of oil. Tar sands and another process called fracking, which enables you to get oil and gas from shaft, from rocks, really. Now, it turns out with coal is also expected to go up. Why is that? Well, it turns out that the U.S. and China have a lot of coal. In fact, the U.S. is often called the Saudi Arabia of coal. We've got a lot. And when it comes to an energy crisis, you can be sure if you got a lot, like China's already burning a lot of coal. We used to burn a fair amount of coal. It's very controversial in the US. And then there's also gas, that's going to go up. There's a problem with all three of those. When you burn them, you get CO2. CO2 contributes to global warming. So we've got to do something about that. And nuclear is a problem because even with fission, there's people don't like it because it's dangerous. There can be accidents. For example, in Fukushima, I just read in the Japan Times, English translation of the Japan Times, that radioactive cesium was found off the coast, increase in radioactive cesium found off the coast of Japan in the bay, but it's not dangerous levels. Nuclear fusion would be great, but it's really hard to contain nuclear. This is like doing solar energy, what the sun does. It's very hard to contain that, but there are people are still looking at it, and it could be very valuable if it works. Fission also has the problem, after you use it, you have radioactive materials you have to get rid of or store in some way. So renewables are a great way to go. And renewables will last forever. These will eventually run out. And renewables means you can keep redoing them. For example, hydroelectric dams are an excellent way. Wind, geothermal, solar, photovoltaics, and thermal are great ways. But look at this. There's relatively little increase in the amount here. And why is that? Well, that's because we need people like you making new discoveries. We're working in this area, but we need new young people that have good ideas. And to be able to do this, that will help do two things. It means that we'll be able to, forever, to be able to have the energy that we need in the world and not create CO2, avoid CO2. There's one here that's biomass. When you burn biomass, you get CO2. But to get biomass, you use CO2, so some people claim that that may be an okay way. And here's another thing that people talked about. It's an interesting story. I don't know if you heard this one. But it turns out that natural gas is mainly methane. And methane with ice forms hydrates, methane hydrates. They're found in the ocean, generally in cold areas. So around Siberia, there are a lot of these methane hydrates. Initially, people were worried that with global warming, that these, the ocean would warm up and these would decompose. The ice would melt and the methane would come out. Methane is even worse of a greenhouse gas than CO2. But now somebody has the idea that, well, wait a minute, maybe we can mine these, and this shows, this is the methane ice burning. And that if you mine it, it's another way to get gas, just like natural gas, and that's a good way to keep them from these so-called tipping points. When you get to certain temperatures, what's believed is the temperature goes higher even faster because now you release all the methane. Well, if you could trap it and use it, that'd be better than releasing it. Of course, it means if you're burning it, you're getting CO2, so I still don't think it's a good idea. So we're interested in actually using hydrogen. And so are you. So in Japan, you have an institute devoted to hydrogen research. So you've heard of hydrogen cars. And I noticed in Narita that there was a hydrogen filling station. I don't know what they use it for, but there was I was going to take a picture. I think that's great. There's a hydrogen filling station. And hydrogen is really good because it's not a primary source. You don't mine hydrogen. But if you make hydrogen from water, water is hydrogen plus oxygen. You break those apart, you get hydrogen and oxygen. And then if you burn hydrogen with oxygen, you get water back. It's renewable. And no CO2. And furthermore, you don't want to burn it. There's a better way of doing it, so-called fuel cells. I'm not going to go through the details of the fuel cells, but fuel cells are much better. So you've heard about hydrogen cars. That's an internal combustion engine. That's terrible, very inefficient. It's limited by the Carnot cycle. It's a heat engine. So it can never be great. And, but fuel cells are not heat engines. And so they're not limited by the Carnot cycle. They can be much more efficient. So it's a great way to go. You might say, well, but that's pie in the sky. These are all known. The fuel cells, hydrogen fuel cells, were developed by the NASA space program, part of the Apollo program. They work wonderfully, but they were used for space. And as you might imagine, the costs are astronomical. And part of the reason for that is that you need platinum as a catalyst to get this to work. So we're working, one of our research areas is to find substitutes for that platinum. Something that's cheap and readily available. And I was looking for this at the airport. This is a hydrogen bus. This runs on hydrogen. There are tanks of hydrogen here. It has a fuel cell. The hydrogen comes in, provides the energy, runs the bus. But you can tell it's expensive because it's a Mercedes-Benz bus. It's not. It's something that one needs to work on to make it realistic. I wanted to get a picture, the picture here of a hydrogen fueling station. This is one found in Iceland. So what else can you do with chemistry? Well, I mentioned that here, one of the research areas is to shine light on something, and then it gives off light. It undergoes luminescence. It could be fluorescence or phosphorescence. And in fact, Shimomura, who worked on jellyfish, which jellyfish, or at least the jellyfish found in a deep part of the ocean, they glow. And they glow because of green fluorescence protein. So he isolated that, and it turns out to be really interesting chemistry. And it's useful because you can make a gene that makes green fluorescent protein. And so he got the Nobel Prize. And you can then label cells. You can make them glow. So here are cells that are glowing because of chemistry. One puts on fluorescence proteins, and you can make them different colors. It's now possible with our chemical understanding. You can change the properties. They don't just glow in one color. You can tune the color. Okay, so this gives you some idea of scale. Because now we're going to talk about materials. And so we're going to start at the meter, and then go to millimeter, micrometer, this is a hair, and then nanometer. So this is a hot area now, the nanometer scale, because when you have materials that have this size, they have new properties that turn out to be useful and interesting. And one of the exciting advances that enable us to understand that, and also surfaces, is the ways we have of visualizing, looking at these things. So on a meter scale, you can just see it with the eye. You can use microscale on the millimeters scale. But to see smaller and smaller, there are these really powerful methods that you'll see some of the results in just a minute. I'm going to pause for questions. Okay. Yes? Yes, sure.
You said that you said that by spectroscopy we can analyze the structure of the molecules.
and even medicine areas. But how can I produce a specific structure medicine or chemical chemistry structure?
Okay, so yeah, these are interfering, so that's why I had to turn this off. So that's another area that I hadn't talked much about, and that's synthesis. So when you have two molecules, say, you can, by knowing their structures, you can predict how they're going to react. And so what you do is you can design a synthesis to make something that you think is going to be interesting. Maybe you did calculations and you want to make this structure. So you can do it now by your predictions of how they're going to react. And very often that works, but sometimes it doesn't. It doesn't work. Now, when it doesn't work, you get really upset because you wanted to make that. But sometimes it leads to a new discovery. That is, the idea that you were using turns out maybe is wrong, or maybe you discovered something completely different that's new. Well, that's great. That's really exciting. So when you make something, okay, that's important, but it also, if you find something new, that could be even more exciting because now the chemistry is a living science. It's evolving. We don't know everything there is to know. We're trying to find out. We only know a very small part. So you're discovering something new. And it may be more powerful, and it could lead to new chemistry. So the Suzuki-Miyaura reaction is a good example in which this was new chemistry that was developed, and it's actually catalytic, which are very hard reactions. Right now, there's a lot of excitement in catalytic. You only need a little bit of something to get the things to react the way you want. And because the catalyst reacts, that gets regenerated, really interesting, hard to predict. And that's actually an exciting area now in being able to do catalytic reactions because they're much less costly, they can be more efficient, you can do things that otherwise can't be done. And the last, I'd say at least half a dozen, if not more, Nobel Prizes in synthesis involve catalytic reactions. And that shows it's an exciting area now and important, and one that's ripe for discovery. I wish I was young. But we're still trying to discover new reactions. And Negishi also got the Nobel Prize for similar reactions. So these are details about some of the powerful new methods for which Nobel Prizes also were given. By the way, the importance of Nobel Prize is really not so much that somebody got the prize. What's really important is it's a discovery that has impact. So it has important consequences. It's a very powerful way, in this case, of getting structures. So I'm not going to go through the details about this, but it's called the scanning electron microscope. This is what it looked like in the old days when it first was done. And here's what it looks like now. And here's what you can see. These are polymer fibers. So polymers that you have, you can look at them and see this. These are cubes of table salt that are small. These are some minerals. These are platelets in components of blood in a pig artery. And this is one of the things that's really powerful. These are nanoparticles, very small particles that you can now actually see what they look like and be able to design them. There's atomic force microscopy. It's based on a different principle. And what that can do is not only can you see things, but you can look at it in depth. This just shows you some of the materials that are used. Here's what you can see. So these again are of the order particle of 10 nanometers, 20 nanometers. They're really small. So these are silica spheres, and you can see the structure of these things. These are carbon nanotubes. And carbon nanotubes are very exciting new materials so actually carbon, I should say something about carbon chemistry. So carbon is a compound, the basis of organic chemistry, but carbon itself is very interesting because carbon itself can be found in different forms. Okay, one of the ways to find carbon is amorphous carbon. Another way to find carbon is graphite. These are layered structures. Another way to find carbon, which my wife particularly likes, is diamonds. She's very partial to that. But it was recently discovered that there's another form of carbon, and C60. There's 60 carbon atoms, and they form what's called buckyball, or fullerenes. The reason it was called buckyball is Buckminster Fuller was an architect that designed what really is a soccer ball, football. And that's what it looks like. But at these various places, you have carbons. There's 60 of them, and that's 5 and 6 membered rings. And you can actually make that. It's a new form of matter. And people then kept looking at carbon, and you can now make these tubes. And these tubes are very interesting because of their conducting properties, and they're really exciting. Now, there's an interesting feature about nanotubes, and here you're looking down on the nanotubes. There's an interesting feature about nanoparticles. So we're actually working in the area as well in a collaboration, and you get a new form of well, it's really a new form of matter. It actually has been known for a while, but you can make new forms that have new properties. And one of the things that we're really interested in doing is making batteries. So another way, I didn't mention this, so converting solar energy into electricity using solar photovoltaics is great. And that probably is very important because the amount of sunlight that hits the Earth's surface in a day is good enough for the world's energy needs for a year. So if you can convert solar energy into electricity, that's great. Three problems. Number one, you can't do it at night, and you can't do it in埼玉today because it's cloudy or rainy. The third problem is electricity is great. You can use it for running things, but if you don't use it, what happens to it? It's gone. So what we want to be able to do is convert electricity, store it. One way to store it is as chemical energy. Store it in chemical bonds, and then you can keep it forever, like in hydrogen, and then get the energy back from the hydrogen when you want it. And on a rainy day, at night, transport it anywhere you want. So that's another interesting feature, and for us, another way to do it is if you can use that electricity to be stored in batteries, and that's why we're interested. One of the reasons we're interested in nanoparticles is it's a way to make lithium-sulfur batteries. So all these little batteries that you have, they're typically lithium. They used to be nickel-cadmium, but now they're lithium batteries. They're lithium metal oxide. If you can make lithium-sulfur batteries, they'd be even better, and that's what we're trying to do. So here's another, looking at biological sample. It's really, again, the images that you get are really spectacular. And I just finished reading a book called The Ghost Map. What the Ghost Map is about is in 1854 in London, there was a cholera plague. People died. And they thought the reason that people died, the theory at the time was the miasma theory. That means bad air. And they thought if they were breathing bad air, that made them sick. And it turns out that cholera is caused by an organism in water. And they were able to figure that out indirectly, which was brilliant work. But they actually looked at the water to see if they could see anything. And they didn't see anything. Why? Because the cholera organism is too small. And it turns out at the time, someone in Italy had actually been able to see it, but they didn't know that. So they deduced that based on a ghost map where people died, that it was not near a water pump. People got their water from these water pumps, and that water was infected owing to a problem with sewage, and it was filled with cholera virus, the organism that causes cholera, and they couldn't see it. Well, now we can see this stuff, so we know that it really isn't bad air. It really is a waterborne organism. So that's what I wanted to tell you about in chemistry and how and why chemistry is exciting and interesting, and that is that in addition to the things I didn't tell you about, and because of time, is some other things that show why it's exciting to do chemistry. It's discovering new things, but also contributing to mankind, making it a better world for all of us. So one good example of that is food. So 8 billion people, that's a lot of people to feed. How are we able to do it? You know, Malthus predicted that that if we had 8 billion people, we'd all be starving because there wouldn't be enough food. And what happened was the Green Revolution. Borlaug found that by using fertilizers, chemical fertilizers, you could grow more food in the same amount of area. And you do that here. Rice paddies are a good example of using chemical fertilizers. So being able to make chemical fertilizers cheaply and using them, because you need a lot to grow this great increase in amount of food, that's really important. Nutrition, what we eat, and the impact on us. And one of the things that's kind of interesting, I think, is these trace. Well, we all know about vitamins. There are also these trace metals that are important. We're actually working on selenium, the chemical biology of selenium. Why do you have to have selenium? Selenium is kind of an unusual thing. And it turns out, from a chemical point of view, it's really exciting. And right now, the big thing in selenium chemistry is you need it. If you don't get enough of it, you die. There actually is a selenium deficiency disease, called Kashan disease, which was studied in China. And you get cardiomyopathy and you die. So you need to eat enough selenium. Usually you get it in your diet. But in this area of China, there isn't enough selenium. It's typically in garlic has a lot of selenium, but also green leafy vegetables also have selenium. Whatever has sulfur, usually there's selenium as long as there's selenium in the soil. But now it turns out that if you give people selenium supplementation, it prevents by 50% 3 types of cancer: colon, lung, and prostate. 3 very major killers. And enjoying food. So there were big breakthroughs in taste, how you taste food. And so we now understand the chemical basis much better for tasting. Nobel Prize, again, was recently given for that. So there's another point which I think is interesting, and that is, so using chemistry, you can solve big problems. It's a central science, so it cuts across, it goes all the way from physics to biology. And how can you do that? Well, one person probably can't. Maybe you're a genius and you can do it, I don't know. But typically, it means people have to work together. So in the old days, chemists all worked separately. Now, they didn't collaborate. But now to solve these big problems, you need collaborations. So that's hard. It sounds easy, you know, get a few friends together and collaborate. It turns out physicists talk differently than chemists. Chemists talk differently than biologists. So it's really hard to communicate. That's a major challenge. But when you're young, you can do it, and you can learn how to do it. And we collaborate a lot, and I can tell you, it's not easy. But it's a lot of fun, because you can hear what somebody says, and one of the things that's really nice about science is when people think differently. Because you get an idea, oh gee, that's another way to think about it, and it becomes exciting, becomes useful, and you can solve really big problems. So you should, I hope that you'll find science attractive, and at least learn about it. Even become a politician, you should know something about science. What you can do with it, what you can't do with it, what the impact would be, because if you're a politician, you can determine how much science is going to be done by appropriation things. But even, I think everybody in this day and age should know something about science, because it has so much of an impact on us. And I don't like the idea that science should be reserved to scientists. It's sort of like the high priests. You know, they know what's going on, and everybody else has no idea. I think everybody should know something about science and know what is real and what you can do with it, what you can't do with it. And I think by and large, these are exciting times for science, and hopefully you'll take more science courses if you're ready taking science courses, or look into science courses, because it's kind of exciting, and you can help the whole world by doing it. So any other questions that I can answer, or try to answer?
One available ways of using fluorines. What useful ways of fluorine is?
Useful ways of
Fluorine.
Oh, fullerene. Oh, sorry. So fullerene is an interesting substance because it turns out that there were some chemists, so these are 60 carbons that are attached to each other. And synthetic chemists want to make these. In fact, a very clever idea was one in which somebody by the name of Woodward, who got the Nobel Prize for synthesis, made half of it, and he thought it'd be fun to put the two halves together, just as an idea. And a number of people had worked on it and weren't able to make it. It turns out that a physicist was able to synthesize C60, and his name was Don Huffman, and he's at the University of Arizona. When the Nobel Prize was given for C60, he was probably number 4, and you only give it to a maximum of 3 people. Well, at any rate, what he did was he was interested in the dark matter that's found in the universe. So he thought that it might be soot, just carbon, amorphous carbon. So he was actually trying to make that and determine the spectroscopic properties. And this is where spectroscopy turned out to be really interesting. So we actually put this into, it turns out the key thing was actually mass spectrometry, which is not a spectroscopic method. He was using spectroscopy. He found a purple substance that he was able to isolate. In a mass spectrum, it had the molecular weight of C60. You could see it. And he was the one that first made it. It's a really tricky business. So we actually had carbon electrodes that discharge, and they formed this carbon that vaporized the carbon, and the carbon apparently built up. You had to have the right amount of helium gas present, 2% or something, and you formed this C60. And he wasn't trying to do that. This just shows you that sometimes you can be lucky. And he was looking at another field, and he was the first one to synthesize it. And this method is now commercialized. He actually set up a company called Mirror, which actually makes it. It's actually not hard to make. In fact, my youngest son has a science fair project. He tried to find it in nature. The idea was, well, you should be able to form it in nature. And so he was looking for it. He was trying to isolate everything that had carbon. He was trying to isolate C60 from it. And actually, Professor Huffman was helping him. And he didn't find it. He was looking. It's really exciting, and it has these remarkable properties. And I always say it's sort of a shame on every synthetic organic chemist that the total synthesis of a very important carbon molecule was done by a physicist. So Don's a very nice guy, and he thinks that's funny. I'm not sure a synthetic organic chemist think it's so funny, but there were a number that were working on it. And the problem was, he had really a one-step synthesis of a very complicated molecule. Other people were trying to put it together one bond at a time, or at least a few bonds at a time. And that shows you sometimes serendipity works. That you're trying to do something else, you make this wonderful new discovery.
Thank you very much for ranging from a wide range of science and social programs. Your talk must encourage the audience to create a new science.
I hope so.
And, it's time to close your lecture. Okay. So.
That's good.
写真を撮りたいのでちょっと待って。
いや、私は